Last time we talked about thrust and what controls thrust. This time we're going to talk about this thing called the rocket equation, which helps us determine what the capabilities of a rocket are. Last time we talked about that when the rocket starts taking off, its acceleration increases as a function of time because it becomes lighter and lighter and lighter. And that makes calculating how much velocity it can achieve a little bit complicated. So we're going to talk about that today. This concept was actually discovered by this scientist named Konstantin Tsiolkovsky in Russia back in 1903. And he developed the rocket equation. Now, if we think about this, 1903 was before modern rockets were actually invented. Modern rockets were invented in World War II in about 1940-44-ish. And so he did all of this work that I'm going to talk about in the next few slides before modern rockets were actually invented at all. He just thought of this stuff in his head and then came up with these equations. So let's talk about this fundamental concept called delta V. That is the change in velocity that we need to do things. So the first thing that we're going to talk about is low Earth orbit. You have a rocket that is sitting at Cape Canaveral in Florida. It's moving with roughly zero velocity. All right, it's sitting on the launch pad. It's not moving at all. When it's in orbit, it's actually moving with a speed of about 27,360 kilometers per hour, which in metric units is 7,600 meters per second. It's moving very, very, very fast. This is for low Earth orbit, and it's rough, 7,600 meters per second. Now, let's say that you have a rocket that you want to escape Earth's gravity, and it needs to go to the moon, or it needs to go to Mars or something like that. The first thing it has to do is escape gravity. And the velocity for escaping gravity is equal to 11.2 kilometers per second, or 40,320 kilometers per hour. All right. And so it starts with zero velocity, and then it eventually has to reach a velocity of 11.2 kilometers per second. So these things that I'm just talking about are called delta velocities, or delta Vs. Going from zero velocity to 11.2 kilometers per second is a delta V of 11.2 kilometers per second. For the low Earth orbit, it was 7,600 meters per second is the delta velocity. So when you want to go into orbit, or you want to escape Earth's gravity, you need to know these delta Vs, and then you need to figure out whether your rocket can actually do them. And so we use the rocket equation to figure this out. The rocket equation helps us determine how much fuel we actually need to maneuver with these delta Vs, or whether our rocket is too small, or whether it's way overpowered for what we need. And so you can size your rocket just right based on the delta Vs that you need. All right, so let's look at this thing called the V2 rocket, which we'll talk about in the history section a lot. This is a nice example because the V2 rocket is a very simple rocket. It's a single stage rocket. So the dry mass of a rocket is the empty rocket with no fuel. All right, so you basically take all the fuel out of the rocket and you measure its mass, and that is called the dry mass. The wet mass, on the other hand, is the mass of the rocket with all of its fuel in there. And that turns out to be the dry mass plus the mass of the fuel. Okay, so the wet mass is the dry mass plus the mass of the fuel. You have wet mass, which is the total mass when you're trying to launch, and then the dry mass is the mass after you've used all of the fuel in the rocket. So the other little bit of information that we need is the exhaust velocity. And recall that we used the exhaust velocity when we were calculating our thrust. So the thrust was the mass flow rate times the exhaust velocity. All right, so the exhaust velocity is that velocity of the stuff coming out of the back end of the rocket. And we thought that a good number for this was about 3,000 meters per second. That's a pretty good rough number for most rockets that exist. So the rocket equation has two forms that we use, and they answer two different questions that we have. All right, so in the first form, we have that the delta V that we're going to get out of the rocket is equal to the exhaust velocity of the rocket times this natural log of the wet mass divided by the dry mass. So the ratio of the wet mass to the dry mass is always larger than 1 because the wet mass is always larger than the dry mass. And we'll talk about ln in just a second. And this equation helps us figure out whether we can perform our delta V that we need, like whether we can get to orbit or whether we can escape the Earth. On the other hand, let's say that we have a delta V that we want to perform. We know that we want to get to orbit, or we know that we want to escape Earth, and then we say, how big of a rocket do we need? Well, that's the wet mass. So then you can calculate the wet mass given the dry mass of the rocket times the exponent, exp, of the delta V that you need divided by the exhaust velocity. So form 2 helps you determine how big of a rocket you need or how much fuel you need in that rocket that you have. Form 1, on the other hand, tells you whether you can perform a maneuver. It tells you the delta V that you're going to get out of a given rocket. So these two forms are sort of mirror images of each other. Let's talk for a second about what ln is and what exp is. If you have a calculator, there's a button. If you have a scientific calculator, there's a button that has ln in it, and there's a button that has exp in it. And these things are called the natural log and the exponential. Okay? They're just mathematical terms. Now, the interesting thing is that in the ln, an ln takes a number and it makes it smaller. So in this equation, this form 1 of the equation, delta V is equal to exhaust velocity times the ln of this mass ratio. It takes that mass ratio, which could be, say 10, and it makes it smaller. It makes it like 3. All right. So that means that basically, you're taking the amount of mass, sort of like you're taking the amount of mass and you're sort of crunching it down. And the delta V that you would like is not necessarily as big as you would expect with such a big rocket or something. It basically says you need more and more and more and more and more fuel to achieve a larger delta V. You need just a gigantic amount of fuel to get some delta V because of this ln thing. On the other hand, the exp takes a number and it makes it much bigger. All right. So what it's basically saying is you have some delta V divided by the exhaust velocity. And as you make that delta V bigger and bigger and bigger, the amount of mass that you need grows what they call exponentially. You take this much delta V, you need this much mass. You take a little bit larger delta V, like to escape Earth, and now you need like this much mass. It's exponential growth. So it grows much faster than you would want, really. How does the rocket equation work? What is the fundamental reason for why this exp and this ln thing exists? Well, if you recall, when you start with a rocket, it's sitting on the launch pad and it's fully fueled. right? It's maximum mass. Then as it starts firing, it starts using that mass, and that mass becomes less and less and less. So the rocket accelerates faster and faster and faster. And the rocket equation takes that fact that the mass is going down with time, and it takes the ratio between how much mass you start with how much mass you end with, and it uses that information to calculate the acceleration and the total delta V that you'll actually get from the equation. Okay? It actually is using conservation of momentum to do this. So an example of the rocket equation is the V2 rocket. So the V2 rocket was the first modern rocket ever created. So when we talk about an exhaust velocity that's roughly 3,000 meters per second, that's sort of modern rockets, and it's sort of a nominal value. Well, the V2 rocket was the first rocket, and so its exhaust velocity wasn't that large. It was about 2,000 meters per second. Still the same order of magnitude, 2,000 compared to 3,000, but a little bit less. The dry mass, so the empty mass of the V2 rocket was about 4,000 kilograms, and the wet mass with full fuel and everything was about 12,800 kilograms. If you plug that in to the rocket equation and you do all the calculations on your calculator and everything, you get a delta V from the rocket, from the V2 rocket, that's about 2,358 meters per second. All right, so the V2 rocket can accelerate. It can go from 0 to 2,358 meters per second. Well, orbital velocity, as we talked about just a few slides ago, is about 7,600 meters per second. And 2,358 meters per second is significantly smaller than 7,600 meters per second. So the V2 rocket had no chance of ever getting into orbit. It basically just can't produce enough delta V to get into orbit. It was a ballistic missile. So it went up and it came back down. Okay? So we can calculate, using the ballistic trajectory equations, how far that missile could go based on this 2,358 meters per second. In summary, the rocket equation is an extension of the thrust equation. It helps us determine the capabilities of different rockets. It helps us figure out how much delta V a rocket is capable of producing. Or it can help you determine how much fuel you need to add to a rocket to perform a specific type of delta V maneuver. We can also use it to help us show how stages in rockets are a useful thing. And we'll talk about that in an upcoming lecture. Now, we went through a lot of math today, and we're not really expecting you to be able to do all of that math. What we're just trying to do is demonstrate how you would do that math, like if you actually wanted to do those calculations. We're not expecting you to be able to do those calculations, just sort of understand the concepts behind those equations. So thank you very much.